All right, so hello everyone. Today we'd love to talk to you about Delta Lake and one of, I would say, like the key component of Delta Lake, its transaction log. We're going to go into the details of what's in the transaction log and how it works. So before we start, I just want to introduce ourselves. Who are we? Kind of like a philosophical question, but I'm a software engineer at Databricks. I'm a Spark committer, and I've been working on Delta Lake for about 3 years now. We open sourced it last year, April, so it's been almost a year since we open sourced it. And here we are. Denny?
Thank you very much. I'm a developer advocate at Databricks. I've been working with Apache Spark since 0.5. There you go, a bunch of other stuff. But basically, I'm your resident data engineering geek that talks way too much. So that pretty much covers me.
All right. So today, the way we want to introduce Delta's transaction log to you is first we'll go into the details of the transaction log, what's in the commit, how does optimistic concurrency control work? And then, we're going to talk about a cool feature that, having such a, multi-version transaction log provides you, which is time travel, and we'll try to show it all in action through a demo. But before we start, I just want to, I believe everyone knows what Delta Lake is, but, in a very short way to explain it before we go into the details, Delta Lake is a file protocol built on this transaction log that gives you transactionality as well as schema enforcement, as well as automated file management on top of files that you store in your data lake. So the transaction log is the key piece here. And to show you how it works, when you create a Delta table, this is what it looks like on disk. All right, so let's say that you have a table at a directory called my table. You have the transaction log directory, which is called _delta_log within the root of the table. That's how we identify that a delta, this table is a delta table through the existence of this directory. Within this directory, you'll see multiple versions of JSON files. These are numbered 0 to long.max value. And these contain all the changes that you make to your Delta table. Then optionally, if your table, there's the concept of partitioning where you coarse grain index your data through some common values of your data set. For example, here with date, we could have partition directories where your files may live in. And then you also observe your files within these partition directories or at the root of your table if your table is not partitioned. And Delta underneath the hood uses open source Parquet. There's nothing special about these Parquet files. The key piece here is that Delta's transaction log knows exactly which files to read. So what exists in these JSON files? You see we have several actions that we call within these JSON files. These actions are metadata. So the metadata includes the information of the name of the table, the schema of the table, the partitioning of the table, and any kind of table properties that you may have around this table. We have add file actions, which means that, okay, this is a file that has been committed to this table. So this file may contain statistics. This add file action will contain the size of the file, and also like when it was last modified and whatnot. We have the remove file actions. So one of the key pieces of Delta is that it provides ACID transactions. And one of the key things here is with ACID transactions, you need isolation. And what that means is if you're running a query and some other operation is mutating your table, the query should run on an isolated snapshot of your data. And for that reason, when we're deleting records, or when we're deleting files from your table, we can't actually physically delete them immediately. We just logically delete them with this remove file action. Then we have a set transaction action. This is used for structured streaming. Whenever you're committing files to your table through structured streaming, we add new set transaction actions. And the set transaction action just contains the ID of the stream. The ID of your stream exists in the checkpoint location of your stream. And it also contains the epoch ID or the batch ID of how many batches it has committed for that stream specifically. So by just using the set transaction action, we can say that, oh, this stream has committed up to batch 35. If it's trying to recommit batch 34, we can just say, oh, we already have that data. You don't need to commit that. Then we also have a protocol version for your Delta tables. This provides kind of guarantees that, if you're using an old Delta Lake client when trying to read from your table, this ensures that your old client or your newer client can actually deal with all the metadata and information within the transaction log of your table. So this is kind of like if you've ever used Kafka, Kafka also has like client versions and a protocol versions. So this is the exact same with Delta. This is just to provide, backwards compatibility, as well as if we're ever breaking forwards compatibility, you know about it. Then we also have some metadata about each commit, and this is contained in the commit info action. And basically, once you get to replay the transaction log, add and subtract all these actions in a linear manner, then the end result is the state of your Delta table. It ends up with the current metadata, the current list of files, the current list of transactions, and the version of your table. So we talked about how Delta provides ACID transactions. The first letter is atomic, so implementing atomicity. How does Delta provide atomicity? So one thing to understand is the transaction log for a Delta table is the single source of truth for your Delta table. So any reader that's reading through your Delta table will take a look at the transaction log first. Therefore, changes to the table are stored as ordered atomic units called commits. So here we have 0.json. And then once you make new changes to your table, they will appear as 1.json. When you're querying your Delta table, this 1.json contains all the changes since version 0 of your table. Since this file appears suddenly and atomically, you will be able to read this file to see what has changed in your Delta table, even though there might be new files appearing in the background or files being deleted in the background. So we can say here that, in the first version, let's say, 2 files were added, 1.parquet and 2.parquet. And in the second version, we say that we removed 1.parquet, removed 2.parquet. We did some compaction process to add back 3.parquet. So how would this work? As we play these list of actions linearly in order, the removes will cancel the adds, and we will end up with the final state of the table being there's a single file in this table called 3.parquet. Another key piece here that, a guarantee that Delta requires is mutual exclusion. So we need to agree on the order of changes, even when there are multiple writers. And this provides a guarantee in databases called serializability. The fact that even though things are happening concurrently, you could play them as if they happened in a synchronous ordered manner. So we have 0.json. You could have 2 writers trying to write 1.json and 2.json. So you have user 1 that reads 0. You have user 2 that reads 1. As you're trying to commit user 2.json, user 2 wins. And user one takes a look and sees that, oh, 2.json is already there due to this requirement of mutual exclusion. Therefore, it will have to say, oh, this commit failed. Let me try to commit 3.json instead. So how does that work? Within Delta, within databases, there are two modes of concurrency where you can have pessimistic concurrency or optimistic concurrency. Within Delta, what one means is with pessimistic, you think that there are always going to be transaction conflicts. So in order to provide the best user experience, you lock your entire table as you're doing your transactions. Within Delta, we chose optimistic concurrency because with big data workloads, you tend to append more data to your table rather than having like multiple writers consistently trying to update the same records. Updating the same records is typically rare, at least concurrently. So the way that optimistic concurrency works is that we first record the start version, then we record the reads and writes of that version, and then we try to attempt to commit. And if someone else wins, you have to check all the changes that have happened since your read version and see if anything changed with regards to what you read. So if in the cases where, if there are two appends coming in at the exact same time, since you didn't read anything, what would happen is you would have two writers. They would write out the data files first. Then one writer will make the commit and say that, okay, I've got all these ads. Then you have your second writer, which already wrote out all the data files, but it sees, oh, there's already a commit that I wanted to commit at. So commit version 2 has already made it in. I need to check what changed in commit version 2. So it reads what happened in commit version 2, sees that, oh, all of those were appends. I'm also a pure append. I don't care. So it just says, let me just commit version 0.3. It doesn't have to rewrite any files. It doesn't have to redo the entire computation again. It just automatically commits version 3. In other cases, if you see that, it's kind of like a compaction process. If you have like two compaction processes running at the exact same time, and then you notice, oh, some other process deleted what I was supposed to delete, then it will throw an exception. So here, for example, we see user 1 and user 2 reading the schema. They're both going to be appends. User 1 wins commit version 1, user 2 can automatically commit version 2. So with regards to, how Delta scales is that, since we're dealing with big data, we have a ton of files, we could have tons of partitions as well. How do we scale the metadata? Because they're just stored in, as JSON files. So what we do is we use Spark for scaling. So let's say you have all these actions committed through multiple versions of your data. We could read all these JSON files as a Spark job. And then every now and again, every 10 commits, we automatically create a checkpoint that contains the entire state of your table within one Parquet table, within one Parquet file. Then Spark can read this Parquet file, or Spark can read these JSON files, play the actions in a linear order, and see what the latest state of the table is. So this is much better than going into, hitting your Hive metastore to continuously get metadata, because eventually, the Hive metastore will have, thousands of tables, tens of thousands of partitions, and like concurrently hitting this one single, database to answer all these queries, you'll hit bottlenecks. Whereas with Spark, each of your clusters are individual, or each of your processes are individual processes. Each of your tables have their metadata separately. So you have a lot better scaling guarantees when you use Spark on the transaction log. So how does computing the state work? So first of all, let's say that we've made 3 commits, 0, 1, and 2. Spark would read these commits, play them in order, and then it'll cache the version 2 of the table in state, in memory. So whenever you're querying your Delta table, we can use this in-memory representation of your table, which is, only megabytes of data. It's very tiny, to answer all your queries. But what happens when you get new data? So you were on version 2. What you do is you start listing your table, and then you see all these new versions pop up. So let's say that 5 commits have been made since you last queried your table. So the latest version of the table is version 7. So what we do is we call a method called list_from, which is in Delta's log store implementation. It lists all the changes since version 2. Then we input all these new JSON files as well as the cached version into Spark, play them in order, and then we can cache version 7 on top of it. Then when you're at 7, let's say 5 more commits made it in. As you can see, this time we have a checkpoint file that happened, at the 10th commit. This checkpoint file contains all your changes. All the changes since version 10. So when we list from version 7, what we're going to see is, oh, there's a checkpoint file, and then there are 2 more versions after that. So what we're going to do is we're going to actually forget about the cache version. We're going to read checkpoint 10, and then add versions 11 and 12 on top of it, and cache version 12 to this. So this makes it a lot easier and a lot faster to update Delta state in such cases. So that was kind of like a brief overview of how Delta's transaction log works. And as you can see, we've had all these versions and of the table. So one of the cool things that this versioning multi-version table provides is time travel. So let's talk about how that works. So let's say that we're going to time travel by version. With Delta, you can time travel by versions of your table as well as timestamps. So you can run a query called select star from my table version as of 1071, or you can provide @syntax with 1071 within Databricks runtime to query your table. Or you can use data frame API such as version as of, or you can provide the @syntax within your path to specify which version that you want to load. And once you specify this version, it's very simple to just say, delta log.get snapshot at 1071. And the computation that you just saw just happens very naturally. We can list all the files, see what's the latest checkpoint. We can see version 1070 at having a checkpoint, play the one commit right after it, and come out to version 1071. When you're time traveling by timestamp, then the case happens is that you can't just call get snapshot at 1071. You need to figure out, which version that timestamp corresponds to within your table. To explain this concept, I'm gonna use some data from the Middle Ages. Let's say that you want to understand which version of your table is running at 1492, 1028, which is when the Americas was discovered by Christopher Columbus. So you might write timestamp as of 1492, 1028, and try to load it. So what happens underneath the hood? So we take a look at all your commits, and all your commit timestamps come from storage system modification timestamps. What does this mean? If you use HDFS and you write a file to HDFS, it assigns a modification timestamp to your commit file. Same thing with Amazon S3, same thing with Azure Data Lake. So we use these timestamps as kind of, the source of truth of when these commits made it into your delta table. But the problem is these are distributed systems, and distributed systems can definitely have clock skew. So in this example, I've kind of used Turkish history to demonstrate this, timestamps. 375 was when the Turks migrated from Central Asia into Europe and Anatolia, or towards the west, instead of staying in Central Asia. And that was the beginning of the Middle Ages. 1453 is when Istanbul was conquered by the Turks or the Ottomans. And in the West, they generally treat this as like the fall of Constantinople, but we, treat it as the conqueror of Istanbul. 1923 is when the Turkish Republic came to be. And 1920 was when the parliament of the Turkish Republic was first opened. So as you can see, there's some inconsistency between when the parliament opened and when the republic was, when the republic came to be. So how do we deal with this? Since timestamps can be out of order, we have to list all these commits, and we adjust these timestamps by adding 1 millisecond to any timestamp that's out of order. So as you can see, version 1073 will suddenly have 1 millisecond after the 1923 version. Then when we're trying to find, when was 1492 within these list of commits, we look at the latest version that has the closest timestamp that doesn't exceed the given timestamp. So as you can see, 1453 happened right before 1492. And we can therefore choose version 1071 to actually understand which version that we have to load. And then we can call delta log get snapshot at 1071 to replay that timestamp. So kind of limitations with time travel. First of all, it requires transaction log files to exist. With Delta, we keep by default 30 days worth of transaction logs. 30 days worth of logs in changes for auditing purposes. And these can be modified by the log retention duration configuration within Delta. It requires the data files to exist because as you do compactions, you logically remove old files. But once you call vacuum on your table to delete these logically deleted files, you lose the chance or opportunity to go back in time and read those files. So to prevent that, you can also set like a deleted file retention duration equal to your log retention duration to maintain full compatibility of the entire history that you can time travel to. The thing here is that time traveling in order of months and years is infeasible. And the reason for that is your storage costs will just explode. So if you want to be able to, go back in time to see how a record, what a record was, a year ago or 2 years ago or 10 years ago even, then, you have to change your architecture in such a way, whereas like you can store your data in SCD type 2 format, for example, which retains the entire history of all the changes to each of your records. But when you query the data, it always shows you the latest value, thanks to like a Boolean flag, which is part of your table schema. So do not use time travel for years and years worth of history. Time travel is kind of, the way we built it initially was to prevent mistakes from happening, because we've observed a lot of users, first-time users, misusing Delta and accidentally deleting all their data. With time travel, you could very easily, restore all your deleted data, because it wasn't actually like really physically deleted. And another reason is that computing Delta's state won't scale when you're deleting data. If you're trying to, contain years worth of history. And the reason for that is we delete checkpoint files a little more aggressively. Therefore, you might end up with cases where you might have to load one checkpoint file and 100,000 JSON files. So if you do need history, there are architectural, means of better storing all that history. So that was me talking a lot, and I'd like to hand it off to Denny to show you all of this in action. So I'm gonna stop sharing my screen now.
Perfect. Thanks a lot, Burak. I appreciate it. If you have any questions, please plop them in the Q&A. But I will not answer any questions on Turkish history. That was awesome. All right, so diving right into it, I'm going to go ahead and present my screen. I will show you Chrome. And all right, so give me a second, sorry, as I try to, there you go. Okay, so this notebook is just to give you some context for everybody here, it's actually available already, but we will share out this specific version of the notebook shortly, okay? Now, this is a version of the Delta Lake tutorial from Spark and AI Summit from 2019 in Europe. But what we're doing now is we've done a modified version specifically for this talk, okay? And so, as you say, diving into Delta Lake, unpacking the transaction log. So I've already started some of the running. Basically, what I've done is I've downloaded some data, specifically which is specifically some loan risk data that we had already generated. Okay, so this is just downloading the file. It's a relatively small file. I've set, in case you want to run this on Databricks Community Edition, you absolutely can. So we've already configured it as such, so that makes it easier. And the first thing we're doing is we're creating a Parquet version of the table. So in other words, we're not going to go ahead and just go to Delta right away. We just want to start with Parquet to give you some context behind what Burak actually was talking about, to give you some context on how does it operate when you just go with Parquet alone, okay? And so I created this Parquet table. I defined a view, loans Parquet here. So hopefully you'll be able to see it. I'm going to zoom one more time so you can see it better. Okay, so loans Parquet, and you'll see the schema of this table. This table has 4 columns: loan ID, funded amount, paid amount, and the state. All right. So how many records do you have? We're just doing a count on that loans Parquet, and what you'll see is 14,705. All right. So that's the number du jour for us today. All right. And as you can tell, I just ran it. So, but now I'm going to go ahead and kick off that structured streaming that Burak had referred to earlier, and giving the context of being able to run structured streaming and batch at the same time, because Delta Lake allows you to do that because it has ACID transactions to protect everything. So let's go ahead and just create this particular function, and let's go ahead and run it. Okay, so what's going on right now is I'm going to go ahead and simply run the stream. It's a write stream, as you can see here. Okay, and give it a couple seconds for it to basically kick in. And as you can tell, the input and processing rate are starting to kick off. And here's the batch duration. All right. So if I was to go ahead and do a count on the same path, now note the fact that I've indicated here Parquet path, format Parquet. But what I'm doing basically is I'm not doing a count on the stream. I'm doing count on the batch. So in fact, I can go ahead and do that, which is pretty nice. Okay. So it's right now telling me 160, but there's a couple of problems here. I'm actually going to address 2 of them. First thing is what happens when I try to add a second stream. Okay, so the exact same function, we're just generating different sets of data, and we're going to write to the same location Parquet path. Okay, so when I do that, basically I'm going to kick off the stream. What you notice is that basically over time, while this stream, there's no input processing rate. There's actually not writing any data. The batch duration is going to go up, but there's actually nothing being written here. Okay, this other stream, this first stream, it's actually writing still. Okay, at 41.5 records per second. Input rate is 5 records per second. Okay, but nothing's happening here. Okay, so it's good that I've got data going in, but I can't put a second stream in. So in other words, if I'm building these data pipelines where I'm actually trying to scale and process multiple threads from multiple sources, or a partition source, and push them down to my table, I can't do that. Okay, so the good news is that there is data going in. but I can only do one stream. So in essence, I've locked my table. All right, that's problem number one. Problem number two is, wait, didn't I just say there was 14,705 rows? Right. So right now, from the last query, I have 410. What happened to all my data? Okay, well, if I look at the schema here, what you'll see here right away is that, the problem that I have is that I do have loan ID, funded amount, paid amount, and Azure State, the 4 columns that I originally started off with. But I'm actually missing, but I've actually have 2 additional columns, timestamp and value. So this is cool in terms of I have the timestamp of when this data went in, but it's not cool because I just basically corrupted my table for all intents and purposes. I don't have the actual count that I wanted. So this isn't good. All right. So I'm going to stop all the streams right now. But basically what it comes down to is because I'm using a Parquet table, I can't actually run multiple streams against my table at the same time. Okay. Nor can I, once there's a schema change, it basically in essence corrupts the data that I have. Okay. So both are pretty not fun options. Okay. And common enough when you're working within any data engineering pipelines. Okay, so let's go ahead and do this now with Delta Lake. So I'm going to rerun this particular portion of, again, this is just recreating the views, except I'm cleaning it up and I'm going to create a loans delta. Okay, and so when I run this again, you'll see the same 14,705. So that's a good starting point. Okay, and again, when we look at the data, there are the 4 columns that we're working with. Okay, so perfect. All right, so we're back in action. We're using a delta table instead of a Parquet table. Okay, but then can we do the things that Burak had just mentioned? All right, well, let's go ahead and start talking about a little bit about schema enforcement. By the way, as I talk about schema enforcement, I'm only going to talk about it a little bit. In fact, Andreas and myself will have a session next week where we dive into schema enforcement and schema evolution. Okay, so we're just going to cover a little bit here just to give you some context, but we're going to dive in much deeper in the next session. So just a little call out for ourselves. Okay, so I've created the view. Now note that I'm actually creating a view called loans delta stream, okay, off this delta path location. Okay, so it's one file system location that in which I'm creating a view that's for streaming purposes. Okay, so I'm now going to do a count against that, and it's basically trying to process the data. Okay, so it's just simply trying to do a count off that that file path, the delta path location here. So now I'm going to go ahead and try to run that same code again. Remember, it tried to put 2 additional columns. The reason it did is because by definition, when you run a stream, it'll actually add those timestamp value columns automatically. Aha! But there is now a schema mismatch. So this is the one of the cool things about Delta Lake right away is that there is schema enforcement. It'll protect the table right from the get-go. So it doesn't allow this function to write to that same table because there's a schema mismatch. In fact, if you open up the error message, it tells you right from the get-go that if I want to enable to merge a schema, again, we'll talk more about this in the next session, but I just have to turn on this option where schema is true. Okay, and here's the reason for the difference. Basically, the original table schema has these 4 columns, but the data schema that we're trying to write to has 6 columns. So you can go ahead and basically, if you were to change it or you were to turn on option merge schema, then you're good to go. All right, but let's go rewrite the function. So all we did is basically add this particular statement here. So we're saying, let's only write the 4 columns that you see here. All right, let's go run this now. Okay, and now let's go ahead and write this again. So we're going to do the exact same thing as we did before. We're going to go ahead and run, and we're going to run this particular one to basically write to that delta table. Just the same process like we had saw before. So if I open this up, I'll see the input processing rate kick in and per the batch duration. And if I give it a couple seconds, when I scroll back up, you're going to see the numbers change. In fact, it started at 14,705 and now it's already at 14,805. So as you can tell, the first stream is currently writing into this particular table now. So that's great. Oh, boom, now about the 15,805. Perfect. So, but because I have ACID transactions and the transactions that Burak had been talking about to protect the table, I'm actually able to run a second stream. And for that matter, I can run a third one and a fourth one if I want to as well. But for the purpose of the demo, I'm just going to run 2 today. Okay. But again, same idea. As you can tell right away, as opposed to with Parquet, you see the input versus processing rate kick in for this second stream. All right. Right here at 50 records per second input rate and 186.7 records per second for the processing rate. And this is for the second stream and the first stream, same concept. Okay, so both streams are writing to this table at the exact same time. All right, why? As the transactions are protecting it. If I scroll back up, you'll notice that the counts are quickly updating themselves. So now that what you see here is I've got two streams that are writing to the same file system. I've got one stream that's also reading from that same file system. Okay, that's why we're 2505. If I scroll down and run a batch, I'm going to run a batch at the exact same time as well. So now I have a batch count all going at the same time. So concurrently, two write streams, one read stream, and one read batch. Okay, so gives you that flexibility to run multiple things at the same time against your data. All right, so we're going to stop all the streams and we're going to shift over to exactly what Burak had referred to before about that Delta Lake table history. All right. So before we do that, what you'll notice here actually is that remember that the data was sitting in this location, loans delta. Okay. What happens is that there's actually a underscore delta underscore log, okay, folder as well. So if I run that, what you'll see is a bunch of files here. Okay. So here's the 0th file, the JSON. All right. That's the one that actually initially created the table. And for each JSON that's been added, this is the transaction log that you're calling out. And just as Burak noted when he had mentioned before, every 10th one, we go ahead and actually switch over to Parquet to speed things up. Okay. And right now, here we go. Here's the second one because this is the 20th file. And so right now we're on version 21 or 22 while we're of versions of the history for our Delta table. Okay. So you don't have to look at it like this. Okay. You can actually look at it in a much nicer fashion. So we're going to go ahead and actually simply run Delta table history. Okay, so this is just, by the way, to provide you some context, this is actually all the open source code. We happen to be running this on Databricks, but you can actually run this on the OSS code yourself. Okay, and so here are the 22 different versions of your table. Okay, all right, so from the first initial write to all the streaming updates that went into your table. Okay, all 22 versions, just like the file system. And so just as also Burak had noted previously, if I was to look at the file, all inside each JSON is all this commit information, all this metadata, right? The timestamp, the user ID, who I was, who did it, what was the actual operation, the parameters, the append by query ID, isolation levels, the transaction, yada, yada, yada. All this information per each file, right, is all here. So it gives you each batch, each transaction, you understand exactly what's being impacted, what's being appended, what's being modified, what's being changed. Okay, so that's what's inside these JSON files. All right, and then we're going to cover this a little bit more in terms of in some of the future sessions when we do, especially the DML operation where we're doing insert and updates. But just to give you some quick context, just as Burak had noted, I can now with time travel go ahead and say, okay, give me the version. You can do timestamp too, but for the purpose of this demo, I'm just going to do version. And so what's VO1, the data frame here? I'm just simply saying, okay, format delta, give me the table, okay, from that delta path, version 1 versus version 11 versus the current version, okay, whatever that version is. In this case, since we did this live, is version 22. And then as you see here, here's the counts. So initially the table was 14,705. All right, by version 11, there's 18,505 rows inside it. And for the current version, they're currently 24,000. So that's really cool. But just as Burak had noted, how can I actually have all the data still there? Like, after all, you just constantly insert it. Why can I know what did it happen on version 1 versus version 11 versus the current version? Well, it's because there's a lot of files. So I'm actually just going to do a quick query. You're going to see a lot of files here. Okay, so here's all these little files, all these little small Parquet files that have been added right inside that directory. Okay, so it starts off with the the Delta log, like I had mentioned before, but here's all those files. Okay, they're all pretty small, as you can tell. And actually, I'm going to scroll all the way to the bottom. And there's like, here's the initial file that we had created, right, for the initial table creation. But otherwise than that, lots of small little files. So as you can probably guess, this is going to be slow, right? If you keep on adding more and more files into this, this will become a very slow process. Trying to read that data becomes slow. It's a management headache, all that fun stuff. Okay, so how do we avoid that problem? Well, we're going to talk about compaction of files and also vacuuming. All right, so first things first, let's go ahead and compact the files. All right, so in this case, what I'm doing is I'm going to read from that delta path location. Okay, all the files that you just saw there, all the small files. I'm saying explicitly that I'm going to create. I want you to create 4 files. So in other words, repartition the number of files. I want 4. I'm doing this just because in this particular case, a good rule of thumb or a good starting point is that I have 4 worker nodes. So yeah, I'm just going to go with 4, right? And then I have to specify where the data change is false. By default, the data change is true. Okay, so when it's false, it says, okay, no, I'm going to go ahead and actually make changes. I'm not actually going to assume there are no changes to the data, so I can actually cleanly read and actually run the operations, and it won't change the data at all, basically. All right, so I'm going to keep it as the format delta. I'm going to overwrite it in case, and then basically save it to the delta path. Okay, so I'm going to run this now. So what happens here is now I'm quickly going to create 4 new files. All right, literally 4.32 seconds. So that's pretty sweet. Except if I was to go ahead and look at this all over again, I still see a lot of files. Okay. All right. Why do I still see a lot of files? I see a lot of files because, in fact, if I actually just do a count, oops, sorry about that. There we go. They're 329 though. Okay. So, but why are there so many files? Well, the reason why there's so many files is because for snapshot isolation purposes, if there is somebody trying to query the data at the exact same time as I was running that operation, they can still read the old files that are still there before they go ahead and try to read the new files. Okay. So that makes things a lot better from a concurrency perspective, where basically you can have multiple people querying at the same time. They can still go ahead and actually look at the older files while you're making your performing your operations. All right. So, but it's okay. Let me go ahead and just simply clean up that data. Now, do note, in production, this is an anti-pattern. Okay, do not do this in production. By default, when I run a vacuum, what I'm doing is without specifying retention hours equals 0. What I'm doing is I'm saying go ahead and by default remove any older files that are 7 days or older. Okay, you can change that number obviously, but the idea is that by default 7 days or older. I'm going to go ahead and say, nah, don't even bother doing a retention duration check. Just simply set to 0. Okay, so in other words, what I'm saying is that if it's older than now, delete it all. Okay, so the data is still there in terms of the most recent query, but if I was to try to requery the older data, I will actually result in a failure, because while the transaction log has all of this information, the actual data no longer resides. Okay, and how do I show that? Well, let me go back into the file system, and boom, there you go. Now you have only the files, the 4 files. Okay, the 4 files that were generated as part of the compaction. You still have the delta log. So if I was to go ahead and just run this, okay, all the log is still there. All the transactions that you just did are still recorded. So from a GDPR or CCPA or GRC compliance perspective, you still have that information on what happened to the table. But the underlying data no longer exists, as you can tell, because I just vacuumed it out. Okay. So that should cover it for the demo. We do actually, like I said, we have actually these demos available. We're going to be sending this demo out. But if you can't wait the 5 hours for us to go ahead and email this out to you or update it in YouTube, it's okay. You can go to the Spark Summit Europe demo, right, that we had in the Delta repo. But otherwise than that, we will be sending it out. Inside this notebook, we also call out that you can join Delta Lake on GitHub. Obviously, that's where we put a lot of our stuff. Also, the Delta Lake Slack channel. This is where you can ask us tons of questions, and also the public mailing list. Okay. So with that, I did want to leave time for questions. But before I did that, Burak, anything else you want to add?
No, I mean, thank you, Denny. That was great. One thing that I wanted to also stress out, Delta, in order to maintain this mutual exclusion property within its transaction log, has specialized implementations of its log store depending on which storage system you're on. For example, Amazon S3 has eventual consistency and it doesn't have put if absent guarantees. So when you're using Delta on S3, there are special configurations that you have to set, which is all documented in the Delta Lake docs. So please read those. When you're working on local file system or Hadoop distributed file system or Azure Data Lake Gen 2 or HDFS, these provide atomic renames. So there are also special configurations to set for these. So please take a look at all of them.
Cool. Rock on. So for folks who would like to ask questions, could you do your best to please put those questions in the Q&A session as opposed to in the chat, so that way it's easier for us to track them all, okay? So let me start taking a look at it. Actually, hey, Burak, there's a really good question. Let's start with this one. Do you recommend Delta Lake for OLTP-like workloads?
Great question. I would definitely not recommend Delta Lake for OLTP. You can think of Delta more for OLAP use cases and like big data. So think about it this way. You don't want to insert one record at a time or update one record at a time. You want to batch things as much as possible. So to provide this batching, you can use some centralized message buffer like Kafka or Kinesis or Event Hubs to actually batch up, like 10,000 changes or 100,000 changes. Otherwise, one at a time or, several, few at a time, definitely not.
Cool. Rock on. Nothing I can add to that. So that's sweet. There's another good question about, should vacuuming being done offline as opposed to versus there's nothing to stop vacuum from proceeding if someone was reading one of those older files. Is that correct?
Yes. I mean, since we have this like 7-day buffer, you don't need to actually, have vacuum block anything. Vacuum is something that you just do offline, some other process. You can have like some other cluster running it every, once a week or whatnot.
Yeah. And just to add to the point, remember how we said that it was a anti-pattern for us to set retention to 0, right? So this is precisely the point, that the idea that if you run it with retention 0, you're going to delete everything right away, which sort of sucks, right?
Yeah.
So
you would definitely delete things that you were just about to commit to the transaction log, and that would suck. You would just lose data.
Yeah. Oh, so there's another question related to vacuum. So what does vacuum look like in the transaction log? And so, yeah, go for it.
Great question. Vacuum, it doesn't show up in the transaction log because it's not a commit tier table.
Yeah.
So it doesn't change anything about that table.
Right. But do note the fact that, recall that the transaction log basically hasn't changed, okay? But the underlying data has. So in other words, when you run a query against a version that you see in the transaction log, but the file no longer exists in the system, what will end up happening is you'll get an error. Okay. Now, in this case, this is a desired error because you're actually doing exactly what happened. You're removing older data. And as a quick call out, like, this is very useful for debugging purposes, useful for oops scenarios, and even short-term like model drift or short-term, validations. But I would definitely not do this as a longer-term approach, just because exactly as Brock noted, and you could see from the way the file system operated, there's lots of small files, right? Even if I was to do a compaction all the time, I still have a lot of files. So I really don't want that, right? And so this is good for those specific scenarios. I would not try to run this for like 3 years worth of data, right? If you're going to do this for 3 years of data, I would actually snapshot those tables out, save them to cold storage or something akin to that. And then, like, for example, a good example would be like financials, right? Like financial reporting. Okay, fine, fair enough. Then I take a snapshot of the table on the 31st or on the 1st, depending on how you do it, or on the 5th if you need reconciliation time, and then store those files in that table to cold storage so you still have it when you want to query it. But I would not use this as a long-term approach. Okay. Yeah. Let's see. We've probably got time for about 2 more questions. Okay, Burak, because
Yep.
we'll want to close things up. Let's see. Okay. A good question that we'll dive into deeper next session, but I did want to go ahead and call it out now. If there is a schema change apart from adding a column, is there any other way than to reprocess older data with the new schema?
That's a good question. So if you're like if there's a schema change instead of adding a column, so if the columns do not exist as you're appending to your table, those columns will just be, filled as nulls. So that's totally fine. If you're trying to change the data types, we try to, allow certain data type changes, which Parquet allows. And that's only for, shorts, bytes, and ints are stored as ints within Parquet. So you can upcast from one to the other. But you cannot change from int to long, for example. In those cases, Parquet encodes these values differently. Therefore, you would have to either overwrite your entire table, or you can also decide to, create a view on top of your table that would, omit certain columns or whatnot.
Yeah, makes a ton of sense. Okay, so then the final question, when using Delta Lake with structured streaming, we sort of alluded to this before, but let's call it out specifically. You can end up with a lot of small files, just as we've seen. So what do you think is the best way to handle all of this then?
Yep, as Denny showed in the demo, we have the ability to read from your Delta table and write back to your Delta table with the option of data change false. So this just tells Delta that, this transaction is happening. It's only, rearranging the data in a, different layout. It's not changing any of your data. So this has like a lot looser isolation guarantees or when, committing this transaction. So you can use this data change false to reorganize your data. As well as within Databricks, we have more, we try to make this process simpler with, optimize as a function, which, can do other things underneath the hood. But yeah, this like data change false, the ACID transactions is the key here. You can reorganize, rewrite your data in any way that you want. That could give you, better data skipping guarantees, better indexing guarantees, and whatnot.
Perfect. Well, I think that covers it for today. I realize there are a bunch of other questions that we haven't had a chance to answer. Saying this, this video will be propped up onto the YouTube channel, Databricks YouTube channel. And from there, you're more than welcome to continue conversing with us and asking questions there. We'll go ahead and do our best to answer those questions there. We also will send out an email for everybody who registered via Zoom to go ahead and actually that will send you a reminder for both the video and also the notebooks as well. So we're going to put all this information out there, and we'll still continue the conversation online.